You are standing on a world. That world is rotating at more than 1,000 miles per hour. It circles a star, a sphere of nuclear fire, 93 million miles away. That star is only one among hundreds of billions inside a vast spiral galaxy. And that galaxy itself is merely a single island drifting in a cosmic ocean nearly 93 billion light-years across. When most people imagine space, they picture beauty. Soft glowing nebulae, graceful spiral galaxies, black holes encircled by luminous rings of light. It looks serene, orderly, almost peaceful. But the universe is not a quiet place. It is energetic. It is unstable. And in certain regions, the very framework of reality begins to break down. Tonight, we are not exploring postcard astronomy. We are traveling to the parts of the cosmos where galaxies disappear without explanation, where gravity can shred matter down to atoms, where enormous regions exist that should not, according to our expectations, exist at all. And perhaps the most unsettling part? Some of these phenomena are influencing our own galaxy right now. Let's begin with absence. True absence. Roughly 700 million light-years away lies an enormous region known as the Boötes Void. Its diameter spans approximately 330 million light-years. To grasp its scale, imagine placing the entire Milky Way inside it. From that position, you would see almost nothing else. No neighboring galaxy clusters, for hundreds of millions of light-years in every direction. A space that large should contain thousands of galaxies. Instead, it contains only a few dozen. Astronomers first recognized this anomaly in the early 1980s, while mapping the distribution of galaxies across the sky. What they saw was not a gradual thinning of structure. It was a massive gap, a hole in the cosmic map. Under normal circumstances, gravity draws matter together over immense stretches of time. Regions of space grow dense, forming clusters and filaments in a web-like structure. But here, the expected clustering never happened. The region remained strikingly empty. One explanation suggests that smaller voids may have gradually merged, forming one enormous underdense bubble. Yet that scenario still leaves questions. Because over billions of years, gravitational attraction should gradually reduce extreme emptiness. And yet the Boötes Void persists. It is not frightening because it contains nothing. It is frightening because nothingness on that scale challenges how we think cosmic structure forms in the first place. Now consider something even larger. In the faint microwave glow left behind by the Big Bang, known as the cosmic microwave background, astronomers discovered a temperature anomaly, a region slightly colder than the surrounding universe. That cold imprint corresponds to what is called the Eridanus Supervoid, an immense underdense region nearly 1 billion light-years across. The prevailing idea is this: when ancient light travels through a region with fewer galaxies and less gravitational influence, it loses less energy along the way. That difference appears as a subtle cold spot in the background radiation. But not all scientists agree that the supervoid fully accounts for the anomaly, which opens the door to deeper possibilities. Was there a fluctuation in the early universe before inflation smoothed everything out? Could unseen large-scale structures exist beyond what we can detect? Are we missing pieces in our understanding of how gravity shapes the cosmos? When the oldest light in existence behaves in ways that don't fully align with our predictions, it suggests that our cosmological model may not be complete, and that realization is more unsettling than emptiness alone. Now think about motion. The Milky Way is not stationary. It is traveling, along with hundreds of thousands of nearby galaxies, at roughly 600 kilometers per second toward a region we cannot clearly observe. This gravitational influence is known as the Great Attractor. Astronomers inferred its existence by measuring galaxy velocities. Something enormous is exerting its pull, but the source lies behind dense clouds of dust and gas within our own galaxy, blocking direct observation. We detect it indirectly, through motion, like watching objects slide across a surface toward a magnet hidden from view. Further studies revealed an additional twist. The Great Attractor appears to be connected to an even larger structure, the Shapley supercluster. In other words, we are moving towards something that itself is moving towards something even more massive. A chain of gravitational influence stretching across hundreds of millions of light years. We are embedded in a vast cosmic flow, and we have no control over its direction. Now let's focus on an object we can see: black holes. When a massive star exhausts its nuclear fuel, its core can collapse under its own gravity, compressing into a region where escape velocity exceeds the speed of light. The boundary around that region is known as the event horizon. Once crossed, there is no return. To an outside observer, time appears to slow near this boundary. To anything falling inward, space itself curves so sharply that all possible paths lead toward the center. Matter approaching a black hole experiences immense tidal forces, stretched lengthwise and compressed sideways. This process is often described as spaghettification. At the very core lies the most extreme prediction of Einstein's theory: a singularity, a point where density approaches infinity, where space-time curvature becomes infinite, where our mathematical equations no longer produce meaningful answers. General relativity predicts singularities must form. Quantum theory cannot fully explain them. We know they arise from collapse, but what they truly are remains beyond our reach. They are not just unknown, they may be unknowable. At the center of our own galaxy resides Sagittarius A star, a supermassive black hole containing roughly 4 million times the mass of the Sun. It lies about 26,000 light-years away. In 2022, astronomers captured an image of its shadow, confirming its presence. Its event horizon spans approximately 27 million kilometers. Compressing 4 million suns into that space defies ordinary intuition. At present, Sagittarius A* is relatively quiet, but if a surge of matter were to fall inward, it could ignite into an active phase, emitting powerful radiation. X-rays, gamma rays, relativistic jets extending across vast distances. We inhabit a galaxy whose center contains a dormant gravitational engine, and dormant engines can become active. In the distant past, many supermassive black holes were not dormant. They were quasars, brilliant galactic cores fueled by rapidly accreting black holes. Some emitted more light than 1,000 galaxies combined. As matter spirals inward, it forms a superheated accretion disk, radiating intensely. Jets of energized particles can blast outward for millions of light years. If such an object existed near Earth, its radiation could strip away our atmosphere. It could sterilize our planet. Fortunately, most quasars are billions of light years away, glimpses into an earlier cosmic era. But they reveal what black holes are capable of when actively feeding. They are not passive objects. They can become engines of extraordinary energy. Then, there are magnetars, an exotic type of neutron star with magnetic fields trillions of times stronger than Earth's. Fields so intense they can alter atomic structure. In 2004, a flare from a magnetar 50,000 light-years away briefly disturbed Earth's ionosphere. Had it been significantly closer, it might have disrupted satellites or electrical systems. Magnetars are unpredictable and violent. They represent magnetic energy on a scale that borders on unimaginable. Now imagine something more elusive. A black hole wandering through space, not anchored to a galactic center. Rogue black holes can form during stellar explosions or be ejected during galactic collisions. They drift invisibly. We detect them only through subtle gravitational lensing effects. There may be millions of them in the Milky Way. If one were to pass near our solar system, it could perturb planetary orbits, and we might not notice until gravitational effects were already unfolding. No visible signal, just orbital instability and then disruption. In 2008, researchers analyzing data from NASA's WMAP satellite identified an unusual pattern. Galaxy clusters across billions of light-years appeared to be drifting in a common direction, toward a region beyond the observable boundary of the universe. This motion is referred to as the dark flow. If validated, it implies gravitational influence from structures outside what we can currently observe, beyond the cosmic horizon, beyond the reach of light. We do not know what exists there. Yet something may be exerting a pull on our observable universe from beyond our field of view. Finally, consider the limits of observation itself. The observable universe extends about 46.5 billion light-years in every direction. Beyond that, light has not yet had time to reach us since cosmic expansion began. But the universe continues. Galaxies near the boundary are receding so rapidly that, over time, their light will never reach Earth. In trillions of years, distant galaxies will fade beyond detection. Future observers may see only darkness. They may conclude they are alone. We exist in a brief epoch where the universe remains richly visible. That visibility will not last forever. The most frightening aspect of the cosmos is not one specific object. It is the pattern. Enormous voids where matter should have gathered. Invisible forces steering galaxies. Singularities where physics collapses. Motion toward destinations we cannot see. The universe is not arranged for comfort. It is immense. It is indifferent. And much of it lies permanently beyond our reach. We inhabit a rotating planet, orbiting a star, inside a galaxy moving toward an unseen destination, surrounded by phenomena we barely understand. And with every answer we uncover, new questions emerge. The universe is not merely dangerous. It is profoundly mysterious. And that may be the most unsettling reality of all.